constant equation, which I'm going to write down first. And I still have a couple of remarks to make before I start the proof. So J I J J K L is equal to delta J J I L minus delta I L J K J plus delta I K J I L I K I delta I K L J minus delta L J J I K, and all of I J K L can vary from 1 to n. So this is the structure constant equation for the group, a very specific kind of group. The group is SON, where little n can go from 1, 2, 3, 4, 5, all the way to however large you want. So just to kind of set you off, right? Let me just apply this to a couple of situations. First, we already applied this to the group SO3, right? And let's look at the group SO3. So if I write G, which is an element close to the identity, plus epsilon like this in SO3, then because of the requirement of orthogonality, we see that the infinitesimal matrix epsilon has to be an antisymmetric matrix. So it means E trans epsilon transpose is equal to minus epsilon. Okay. Now let's figure out how many independent numbers are here in the epsilon matrix. So the epsilon matrix is going to be like, because it's antisymmetric, all the diagonal elements has to be 0, and so it has just 3 independent elements: epsilon 1, 2, epsilon 1, 3, epsilon 2, 3. All the others here are just negatives of those on the top right. Okay, so for SO3 there are 3 independent elements. Right? So that means there are 3 independent matrices J. Now, what is the matrix? How is the matrix J different from an original 3 by 3 matrix? The matrix J, you see, is in general going to be, each of the Jij is in general going to be an n by n matrix, because the matrix J is supposed to be an n-dimensional representation of the group SO3. Now, n can be, depending on the particular group, let's say the group is SO3, you can actually figure out how many irreducible independent representations are there. We indicated last time that for SO3, there are infinitely many representations depending on what is in quantum mechanics called the total angular momentum. So in quantum mechanics, J is equal to 1/2, 1, 3/2, 2, 5/2, and so on and so forth. Okay? And the size of the representation of all the irreducible representations is in general 2J plus 1. So the representation corresponding to total J equal to 1/2 is a 2 by 2 matrix. Okay? The representation for J equal to 1 is a 3 by 3 matrix. the representation for J equal to 3/2 is a 2J plus 1 is a 4x4 matrix. The representation for 2 is 2 times 2 is 4. It's a 5x5 matrix, and so on and so forth. Okay. So you can have a 2x2 representation, a 3x3 representation, a 4x4 representation, a 5x5 representation in general, and n by n representation. Okay. And for each of the independent epsilon ij's, you have an independent jij. So for the case SO3, how many independent jij's are there? So you just have, corresponding to these, so you just have the 3 n by n matrices, J12, J13, and then J23. That's it. Okay? Corresponding to each of the independent parameters of the group SO3, you have one such representation matrix. Yeah?
Just to go back real quick, where did you get 2J plus 1 come from?
Oh, this is from quantum mechanics. This is a result that I'm quoting to you now. Never mind how it's proved. We're going to
it's the M.
total. It's a total angular momentum quantum number, and the 2J plus 1 is all the possible M values.
Okay.
Okay. So many of you probably have heard about that already. But this situation only corresponds to the SO3 case, because the SO3 is the infinitesimal generators for rotations. Okay. So you use the total, and for rotations, the angular momenta are the conserved quantities. And so, they are the infinitesimal generators for the rotation group, as we have seen. Okay? So this is the thing to remember right now, right? You start off with a certain group SON, where in this case n is equal to 3. Then you can figure out how many independent parameters there are for that group. There are as many j's as there are independent parameters. Okay? So if there are 3 independent epsilons, then there are 3 independent j's. And we name those j's in the same way that we name these epsilons in here. But the thing you have to remember is that each of the epsilons is just a number, right? But each of the j's is an n by n matrix, where it's undetermined at this point what big N is. But you just have to realize that big N is different from little n. Okay? Little n is fixed once the group SON is fixed, right? But big N can have many possible values. So now, one of the possible values of big N happens to be 3 also. So in this case, this is like what's called a fundamental representation, because it's also a 3 by 3, as is the original matrices in SO3. Okay? Now, let me go to another situation, SO4. Now, SO4 is also going to be important in physics applications, as we'll try to show you a little bit later. We know that SO3 is important for physics applications because it corresponds to 3-dimensional rotations, but SO4 is also going to be important. And clearly, SO4 contains something bigger than SO3. So it's an additional symmetry in addition to rotational symmetry. Now, okay? So in this case, little n is equal to 4, if you consider the group SO4. All right? Now, let me ask you, how many independent epsilons are there in this case? 6, eh? Is it 6? Yeah. So you have, this is SO4, so you've got a 4 by 4 matrix. An infinitesimal element in SO4 is always written as 1 plus epsilon. Well, 1 is the identity 4 by 4 matrix, and this is going to be an antisymmetric matrix. Okay? So, as you said, you have 4 independent ones, so it's epsilon 1, 2, epsilon 1, 3, epsilon 1, 4, epsilon 2, 3, epsilon 2, 4, and epsilon 3, 4. So you have 1, 2, 3, 4, 5, 6 independent epsilons, and so you then have 6 independent j's also. So the 6 independent j's would be J12, J13, J14, J23, J24, and then finally J34. Now, you view each of these as in general an n, big N by big N matrix, okay? So each of these of these is a big N by big N matrix where we don't know as yet what big N is. There are many possibilities because there are many different so-called irreducible representations for the same group. Okay, so, but whatever it is, whatever big N is, the different Jij's always obey this so-called multiplication rule in the Lie algebra. Okay? Let's pick an example. So I want to find out, so what does this rule tell you? This rule gives you a multiplication table for these 6 matrices, if you will. If this is treated as a multiplication, okay? Remember in matrix algebra, the commutator is regarded as some multiplication, okay? Because the Lie algebra is also a vector space, so that a linear sum of all the, in fact, each of these can be represented as a basis vector in the 6-dimensional linear vector space. That is the Lie algebra corresponding to the Lie group SO4. Okay? So the point is, if you take any of these two and commutator them together, the result is going to be a linear combination of the same 6, which gives you another element in the same linear vector space. Okay? So that's why the entire Lie algebra can be represented as can be viewed as it is in fact a linear vector space. But on top of that, it also has an imposed multiplication rule which makes it an algebra. Okay? So that's why it's called a Lie algebra. So, well, why don't you pick 2 of these and I'll show you how to apply this. Okay? Pick any 2 for me. Yeah.
So this commutator of the Jij and JKL gives us a multiplication rule?
Yeah, that's a multiplication rule between these 2 objects.
And that tells us that SO4 would be a Lie algebra?
Well, because this particular multiplication rule obeys the 3 rules for the Lie algebra, one of them being the Jacobi identity that we identified last time, the other one being the distributive rule, and then there's also an anti-commutative rule and so on. Once any multiplication rule satisfies those 3, then that set of objects that can be multiplied together with this rule is called a Lie algebra. In particular, the infinitesimal generators of a particular Lie group form the basis of a particular Lie algebra corresponding to that Lie group. Okay? So as we said before, corresponding to the group SON, we have the Lie algebra, which is simply written as script S script O4. That is the Lie algebra corresponding to the group SO4. Okay? All right, let's get back to this in here. Now you pick any 2 out of these, right? Why don't we pick, which 2 would you like? The first one and the last one?
Yeah.
Let's see how to multiply together, okay? So we're going to try to multiply together J1, 2 and J3, 4. Let's see what that gives us, right? Because that's the first one, that's the last one. Now let's apply this, right? So in this case, let's write down IJKL. What are IJKL here? I and J are 1 and 2, right? K and L are 3 and 4. Is that okay? All right, so what does this rule tell us? According to this rule, this says it's delta Kj. Delta Kj is this guy in here, times JIL. IL is 1, 4. That's the first term. Check me, okay? I'm liable to make mistakes. Okay? So far, so good? Minus, what is it now? Delta IL, so it's 1, 4. J, KJ. KJ. Okay? Plus, plus delta IK. What is IK?
1, 3.
IK 1, 3. And JLJ 4, 2. LJ. LJ. Is that okay? Minus delta LJ for 2 J I K. ik. Well, in this case, it happens to be 0, right? Because all of the deltas are 0. They're Kronecker deltas. Okay? 0 is okay. 0 is just the 0 element in the linear vector space. Okay? So it says these two, in fact, commute with each other because their commutator is equal to 0. What that means is J12 multiplied by J34 is the same as J34 multiplied by J12. They commute with each other. Okay? Now, if you pick two of them which has a common index, then let's say we pick the first one and the third one. Okay? So J12, J14, for example, then you may have some non-zero things happening because what do you have then? In this case, IJKL would be 1, 2, 1, 4. Okay? And so this would be equal to delta. Here we go again. KJ, 1, 2. Now I don't need to multiply. This goes to 0 anyway. First term goes to 0, okay, because of the delta function. And then the second term is delta IL. IL, also 0, right? It's delta 1, 4. Second term is 0 also. The third term is delta IK. This time it's okay. Delta IK is delta 1, 1, which is not 0. And it is multiplied by a J, LJ. LJ is 4, 1. Sorry, 4, 2. Is that okay? LJ is 4, 2. Finally, minus delta LJ, 4, 2, which is also 0. So the whole thing is just J42. Do you see how this multiplication works? Now sometimes you can have more than one term, all right, obviously. But as I said, you can regard these things, each of the 6 different J's, as being a basis vector in the vector space that's spanned by these things. So that a linear combination of these things is also another element in the same vector space, in other words, in the same linear algebra. Okay? So sometimes it may happen that you may have 2 terms, you may have 3 terms, you may have 4 terms, or 4 of them, depending on the indices. Okay? But the interesting thing is, no matter what group it is you're talking about, as long as it's SON, where n can be anything, one and the same structure constant equation governs them all. So this is a very powerful method, powerful result indeed. We saw last time already that for SO3 there are 3 independent JIJs, and those are proportional to the 3 components of the angular momentum. That's why you can produce immediately the commutation relations for the different components of the angular momentum, as you have been studying in, or maybe some of you will be studying in quantum mechanics. Okay? But here you see we have derived it completely by, there's no quantum mechanics here at all. There's just, what is there is just the rotational invariance aspects. We just started off with a group SO3, or SO4, SON. Okay? So with that in mind, now let's get to prove this general result. The proof will take us a little while, but I think it's interesting to go through that because this will show you how, in general, some of these algebraic manipulations will be carried out. So let's try to follow that very carefully. So let's say we start off with some general group SON, and we haven't at all specified what this value of little n is. Okay? Let's say we pick 2 elements, A, B. Both of those are elements in SON. Okay? And I'm going to say these are infinitesimal elements, so that A I can write as the identity plus some small antisymmetric matrix to first order in epsilon. I can stop at the first order again because I'm writing elements that are very close to the identity. Okay? The identity in here being an n by n identity matrix. Okay, so each of these guys is a little n by little n matrix. So this is a little n by little n anti-symmetric matrix. Okay, so now B being a different element, I can write this as 1 plus epsilon prime, where epsilon prime is a different anti-symmetric matrix from epsilon. Is that okay? Just to remind you that I'm only writing things to first order, so I'm ignoring things that are of order epsilon prime square or higher. Okay, that's how we write things in general. And I'm just ignoring these things in here. Okay. Now remember that both epsilon and epsilon prime are antisymmetric. That means epsilon transpose is equal to minus epsilon, and epsilon prime transpose is equal to minus epsilon prime. Both of those are antisymmetric matrices. Now let's say we pick a group homomorphism between SON and a set of big N by big N unitary matrices. Let's say we are talking about a unit. Well, actually, we don't even have to specify the unitarity property at this point. Let's say we pick some representation, okay? Pick some group homomorphism, okay? Let's say we pick some group homomorphism, which means that a group representation, which means that it's a group homomorphism between the original group SON and the group of big N by big N matrices considered as invertible operators acting on a big N dimensional linear vector space. Okay? So corresponding to A, the group homomorphism or the representation takes me, so this little a is a little n by little n matrix. This is a big N by big N matrix. The little n can, of course, be different from big N. Okay? And the same representation takes me from B to U of B. Okay? Well, U is a group homomorphism. Okay? Now, let us construct this expression. Now, if I take B and A, I can form the similarity transformation of A by B, so to speak. Like that. Okay? So, B is in SON, so B minus, of course, is in SON, and A is also in SON, so each one of the three matrices in here is in SON. So by the group property of SON, the product has to be another matrix in SON. All right? So I can represent this matrix by the same representation. And now this being a representation, it has to obey the so-called homomorphism rule, which is what? Which is that the representation of this product must be equal to the product of the representations. Okay? Okay? The representation of a product must be equal to the product of the representations. This is called a group homomorphism rule. Okay? Now, let's first write this group product in terms of the epsilon and epsilon prime first. And so, of course, you see that B inverse A times B is equal to B inverse. And I'm going to write A as 1 plus epsilon plus O epsilon square, which I'm going to ignore, times B. Okay? So ignoring this thing in here, I'm going to have B inverse 1 plus epsilon times B to first order in epsilon. Okay? And that's going to give me something like this. Now, first term, B inverse times B is just equal to 1. Okay? And then what do I have? I have B inverse times epsilon times B. B inverse times epsilon times B. And then I have things that are second order in epsilon, which I'm going to ignore. Is that okay? Right? So far, so good, right? So I'm going to define this thing to be, let me just call this guy epsilon bar. Okay? Epsilon is small, so epsilon bar is going to be small also. Again, to first order in epsilon. Okay? So I have epsilon bar is defined to be B inverse times epsilon times B. But I'm going to write this a little bit differently, taking advantage of the fact that B is an SON. B is an SON, therefore it's an orthogonal matrix. And if it's an orthogonal matrix, inverse must be equal to 1. It's transpose, okay? So I can write it like this. That makes sense? Okay? So we have, in fact, to make use of specific properties of this group, right? Otherwise, everything is quite general up to this point. Here's the first step where we make use of, one of the most important property of this group, which is that it is an orthogonal matrix. Okay? Okay, now, so on the other hand, this whole thing, so I have that result, okay, and let's see, because this is equal to 1 plus, because this guy I have now written as 1 plus epsilon bar, right? So this whole group element I have now written as 1 plus epsilon bar, okay? So I can also write U of B inverse AB is equal to U of 1 plus epsilon bar, okay? And obviously, I can write this as 1 plus a linear combination of all the independent elements in epsilon bar. There are as many independent elements in epsilon bar as there are independent elements in epsilon. So this must be a linear combination of all the independent elements of epsilon bar, the coefficients being what? Some big N by big N matrix, which are the big J's, okay? So I guess the convention is that I'm using a minus sign in here. That's how we wrote it last time. So this must be equal, and we introduce a 1/2 factor to take care of the anti-symmetry properties of these J's. Jij, epsilon bar, Ji. So this is merely a linear combination of these epsilon bars. There are as many J's as there are epsilon bars, so that the big J's can be viewed as a coefficient in this linear combination. But since we are doing a big N by big N representation, each of the J's, as we said before, must be a big N by big N matrix. Okay? So each of these Jij's is a big N by big N matrix. Plus higher order terms, which we are going to ignore. And now we will make use of this property in here. Okay? It's in fact equal to this right hand side. This right hand side I'm going to write as U inverse B, right? We have proved that U of B inverse is the inverse of U of B. That's again a homomorphism result. Now the middle factor in here is U of A. In U of A I can use a similar expression like this. It's 1 minus 1/2. Again, the same Jij's, right? Jij. This time it's just the epsilon itself, because the epsilon are the ones that are the infinitesimal numbers that correspond to A. Okay? That's a middle factor in here. Finally, I just write this as UB like this. Okay? And obviously, plus higher orders in epsilon, which we're going to ignore. So everything can be written as, you multiply these together, you have 1, because this times 1 times this is just 1, minus 1/2 U inverse of B, Ji epsilon Ji times UB. plus higher orders, which we are going to ignore. Okay? So what I have up to this point is that these two things are equal to each other, right? This thing is equal to this thing. Is that okay? All right? Okay? Where the JIJs in both expressions are the same JIJs. Okay? So we are making use of the same big N by big N representation. Okay? See that here we have the epsilon bars, here we have just the epsilons. Okay. Now let us come in with one fact for the epsilon, another fact for the epsilon bars, which we have actually written here already. So let me write a typical element for epsilon bar. Okay. Let me call this beta alpha. Like so. There are many epsilon bars. There are as many epsilon bars as there are epsilons, independent ones. Okay, those are numbers. Okay, and by this expression, so this is like a product of matrices. So this is like BT epsilon B, the beta alpha matrix element. Okay. And using the rules of matrix multiplication, we must have this is equal to BT. Let me write it like this: beta I, epsilon ij. The I is summed over B J alpha. This is matrix multiplication. Do you remember that? Okay. The three matrices to be multiplied together. So you have two pairs of indices to be summed over. All right? Using the rules of matrix multiplication. Okay. Any questions up to this point? Everything seems to be quite straightforward, right? Everything will be straightforward. Yeah?
We can rewrite it to universe instead of U being.
Yeah, we can prove that by homomorphism, I think. So because here's a fact. U of B inverse is equal to the inverse matrix of U of B. You can prove that by homomorphism rule. Okay? Go home and try to prove that. All right, let's see. Okay, now then by 46 is okay, 46 is this. This is equal to that. So we're going to make use of this rule, right? So that means then so minus a half is 1 is the same here, minus a half is the same. So I'm going to replace ij by alpha beta. And so here's what we are going to have. Let me see if you agree with me. Okay. J alpha beta epsilon ij bt of beta I and b of j alpha. Okay. So I'm going to multiply j alpha beta. This is like what? 1/2 of j alpha beta epsilon bar beta alpha, because the alpha beta are just summed over, right? Okay? And so, meanwhile, epsilon bar beta alpha is that. Okay? So I'm just sticking that in here. That's all. Okay? And so that is just this quantity in here. This quantity in here must be equal to this quantity. Right? Take out a minus 1/2. So on the right-hand side, it is equal to epsilon ij. This is just a number. I can move it anywhere I want. And then u inverse beta, b rather. And then j ij, and then ub. Now, you have to be very careful that these three guys are all big N by big N matrices. Okay? So you cannot change the order around. All right? But over here, these three things are all numbers. You can put them anywhere you want. Okay? Whereas this one is an N by N matrix. Okay? So both sides, of course, has to be an N by N matrix. Now, let's manipulate with this equation now. This latest equation that we have obtained. What I'm going to do is to interchange I and j on the left-hand side of the above equation. I can clearly interchange I and j. Why? Because both I and j are summed over. So they're both dummy indices. So instead of writing this as a pair of i's, I can write this as a pair of j's. And instead of writing this as a pair of j's, I can write this as a pair of i's. Okay? So doing that, I will have epsilon ij, like that. Okay? And I will have B transpose. Let me write BI alpha first. BI alpha. So if interchange I and j becomes an I, BI alpha, times BT of, instead of beta I have beta j. You have to do these very carefully. Okay? And finally, it's a j alpha beta. All right? But if you look at the right-hand side, I have an EIJ in that order, lower I, upper j. So E lower I, upper j appears on both sides of the equation now, and therefore I can factor it out. Okay? And taking this to the left-hand side introduces a minus sign. And so I will have inverse of u of b times jij times u of b. That must be equal to 0. Okay? What this says is that this minus that must be equal to 0. That's all. Is that okay? So, I am going to now look at this expression in here, right? Both alpha and beta are summed over, so therefore this is a second-rank tensor with lower index I and upper index j. Okay? Lower index I and upper index j. It's a matrix value tensor, if you will. Each of the components is a matrix. It's an n by n matrix in here. Okay? And I'm just going to call this, define this to be big F ij like that. Okay? Where big F ij is a big N by big N matrix. Okay? So this is a big N by big N matrix. Now, I am going to make a claim, which I will prove subsequently, that this is anti-symmetric. So I will prove that Fij is equal to minus Fji. We'll prove later, let's say. Okay, it'll take a few lines to prove that, but I'm going to defer that for the time being. Okay. We'll prove that a little bit later. At the same time, now, at the same time, this equation, can I take out some of this stuff here? Okay, let me see what, let me take out some of this stuff in here, okay? So let me look at that equation, epsilon ij, epsilon ij, fij. Remember the I and j are summed over here. That equation tells me that that sum is equal to 0. Okay? Now, but we know that this is an antisymmetric matrix, right? The epsilon is an antisymmetric matrix, so that epsilon ij is equal to minus epsilon ji. This is an antisymmetric matrix, okay? So I can write this sum a little bit differently. This is actually two sums, 1 over I and 1 over j, but exploiting the antisymmetric character of epsilon, I can write this as two sums I and j with j always less than I, okay, and split it up into two terms, as I did in my classical mechanics class. How many of you in my classical mechanics class this morning, or last time, you remember we did the same thing? Something like that, okay? See if you agree with me. Write down the epsilon ij, and so you first have fij, okay? So let's say this is only half the terms because I'm only taking j less than I. I have to include, since this is a complete sum, I have to include the other half, which is for j bigger than I, okay? But for j bigger than I can, because it's a sum, I can interchange I and j and switch it to minus, okay? So fji becomes minus epsilon ij, so this becomes, I can stick in a minus sign, and if I interchange I and j, I have something like this. Do you see why? You kind of see why? Go home and mull over it, okay?
It's because you know that you have to switch the epsilon. You have to switch the sign of both the epsilon and the f. We know the epsilon is antisymmetric, so close to each other. So it's just
essentially, in the second sum, you have to have j bigger than I. Okay, that goes here. Yeah. But if you still want to write it as j less than I, you have to flip the indices. Right? Once you flip the indices, the epsilon gets changed in sign. Okay? So you have this situation in here. Okay? Now, this is a sum over all the independent epsilon ij's because j is less than I. Okay? Those are all the independent ones. And so what that tells you is that for any particular value of I and j, this thing within the parentheses must be equal to 0 because all the epsilons are independent. Okay? In other words, fij is also equal to fji. Right? In other words, this implies that fij is also equal to fji. So then we have two separate facts now. Fij is equal to fji, but fij is also equal to minus fji. So that forces you to conclude what? That any fij must be equal to 0. something that's equal to its own negative has to be 0. Okay? Is that okay? So Fij is equal to 0 up to this point. Because of this, the symmetry condition and the anti-symmetry condition that forces us to conclude that for any value of Fij, including the case that I is equal to j, must be equal to 0. Any value of I and j. Fij must be equal to 0. And what is Fij? Fij is defined by this expression in here. Like that. That's the definition of Fij. Okay? So if Fij is equal to 0, then this term must be equal to this term. Okay? There's some difference between those two is equal to Fij. Fij is equal to 0. This must that equal to that. So this implies that, let me write it out again. B, this time we write like this. U inverse, UB inverse times J I J. I lower, J upper times UB must be equal to BI alpha BT beta J and J alpha beta. Okay? All right. Now, so far, now let's make use of this expression for B. Okay, and also the condition that the epsilon prime matrix must also be anti-symmetric. So then, making use of this expression for B, then you have the unitary representation for B can be written like so. Unitary representation for B must be the big N by big N identity matrix minus 1/2 the same J's, alpha beta epsilon prime beta alpha plus order of epsilon prime square, which we are going to ignore. And of course, it's with this linear expansion, it's easy to calculate this inverse, right? The inverse is what? When this minus is replaced by plus. See that? When you multiply the two together, it's the identity. Okay? So that you have the inverse of this must be equal to 1 plus 1/2 the same thing. At least to first order, which is the only order we are keeping up to this point. You see that? When you take these two and multiply them together as matrices, it gives you 1. It gives you the identity. Okay? Because you have plus 1/2 of this minus 1/2 of this, which exactly cancels out. Okay? So the first order is easy to calculate the inverse. And now let's do a couple of more things here. At the same time, taking this, now remember this is for SON, this is an n by n matrix, little n by little n matrix, okay? And so we're going to write the individual matrix elements for B. So let's write BI alpha. Because we have some BI alphas in here, so we want to write that, okay? Is delta I alpha, this corresponds to the identity matrix, plus epsilon prime I alpha, plus higher orders, and now the next thing we want to write down is the transpose of B beta J. transpose of B, the beta jth element of that, we could write this as delta beta j. Okay, obviously the first term for corresponding to identity matrix, but because of the fact that epsilon prime is also antisymmetric, I must write this as, now let me be careful, this is equal to epsilon E prime transpose the beta jth element of that. Okay? But since epsilon prime is antisymmetric, epsilon, the beta jth element of epsilon prime transpose is equal to minus the j beta element of epsilon prime. Okay? So this is equal to delta beta j minus epsilon prime beta j. You have to be very careful with all those indices, okay? Because we are dealing with transposes and so on and so forth. Okay? Because of the fact that epsilon prime is anti-symmetric. Now, so let's put these things together into this equation in here. Let's look at this equation. I'm going to write down using this expression for inverse of u, and then we have the j, and then this expression for u, and then I'm going to use those expressions that I've just written down for the two b's in here. And then we can compare the j's on both sides of the equation. And that's the strategy that we are going to use to get to this final result. Okay? Oh, so let's do that very carefully. Okay, here we go. So for inverse of u, I have 1 plus 1 half j alpha beta epsilon prime beta alpha plus second order jij times u itself, which is this 1 minus 1 half j alpha beta epsilon prime alpha beta plus higher orders, which I am going to ignore, is equal to the right hand side in here, and in the right hand side I'm going to make use of these two expressions for the two b's. Okay? And the b's are just numbers, so I'm going to put them like so, times a matrix in here which is j alpha beta. Okay? And I simply stick these two things in. Okay? This one and this one in here. So it's delta I alpha plus epsilon prime I alpha plus I order terms that I'm going to ignore, delta beta j minus delta prime beta j plus higher order terms that I am going to ignore. Okay? Okay. Now, here's an interesting thing. On the one hand, on the left-hand side, you see, you have j alpha beta. Let's see. Let me be careful in here. Oh, sorry. Here, on the left-hand side, you have, let's multiply 1 times 1, so times this. So the first term is just jij, okay? So the first term is just jij. So let me just take out some space in here. remember now, whenever there are matrices, you have to keep the order in which the matrices appear. The only matrices here are the J's, the Jij's, okay? So you have to keep them in the same order, okay? So the first term is 1 times Jij times 1, which is just Jij. The 1, remember, is an identity matrix, okay? So you have Jij. Now, what are the terms which are proportional to first order in epsilons? You have multiplied this by this. So it's J alpha beta Jij. Okay? But then there's another term which is proportional to the first order in epsilon prime, and that is Jij J alpha beta. But there's a minus sign in here, so there's a commutator between J alpha beta and Jij. Do you see that? Okay? See, one term is J alpha beta multiplied by Jij. The other term is Jij multiplied by J alpha beta. Those are not equal to each other. Since the J's are matrices, they don't commute. And so we can figure out what the commutator is. You see how it works? Okay? Very clever. So you just take out the coefficient, which is 1/2 epsilon prime, beta alpha in each case. And the thing to be multiplied is the commutator of J alpha beta and Jij in that order. Because in the first term, J alpha beta appears first and then the Jij. In the second term, with a minus sign, Jij appears first and then the J alpha beta. So together we have the commutator of those J's. Okay? That's everything to the first order in epsilon prime. And so plus high orders in epsilon prime, which we are going to ignore. And similarly, we're going to play the same game with the right-hand side in here. You see, on the right-hand side, everything within these brackets are numbers, so you can multiply them in any way you want. Okay? And again, you have, you take the first term. This is identity matrix multiplied by J alpha beta. You see alpha and beta are summed over, right? When you string it out, what do you get? Delta I alpha multiplied by delta beta J alpha beta, right? Remember that alpha and beta are summed over. When you sum over alpha, the alpha has to be equal to I. When you sum over beta, beta has to be equal to J. So the whole thing is just what? Jij. Okay? And so again, on the right-hand side, the first term is Jij. This is very nice, because then the Jij's will cancel on both sides. Okay? Then we have to write a second term, which is a little bit more complicated, which is equal to the terms that are proportional to first order in alpha prime, and there are two of those. One of those is, this multiplied by that, and the other one is this multiplied by that, okay? So it produces two separate terms for you. Let's write them out independently. Alpha prime, I alpha, that's this term, multiplied by delta beta J, multiplied by this term, and then multiplied by J alpha beta. Okay. The other term is a minus sign. Okay. You take this one, epsilon prime, beta J, and it goes together with the delta I alpha. Okay. With a minus sign in here. So it's delta I alpha, epsilon prime, beta J alpha beta plus high order terms in epsilon prime. Okay, just multiplication. Okay, multiplying these guys together. And keeping terms only up to first order in epsilon prime. Okay, so both sides is only kept up to first order in epsilon prime. And so because of this fact that this is equal to that, and half is, okay. I have to, so that means what? That means 1/2 times this must be equal to that. Okay, so let me write down that result first, okay? So far we arrive at here. 1/2 epsilon prime alpha beta commutator j alpha beta jij must be equal to everything over here. Now let's do one sum. In fact, we can do the sum over beta in here. Okay, first. When we do the sum over beta, beta must be equal to j, and then you take this away. All right? So that must be equal to epsilon prime I alpha j alpha j. Is that okay? And similarly, you can do the second one. You do the sum over, you do the sum over alpha now, because the alpha sits with the delta, okay? You do the sum over alpha, alpha must be equal to I. And so I have epsilon prime beta j, j I beta, like that. So beta is still sum over. Check that. Is that okay? All right. We are close to where we want because we've got this commutator sitting right over here. That is what we want to try to derive, okay? And in order to beat that down into this form in here, we have to manipulate the right-hand side a little bit more. Just a few more steps, but it's about time to take a break, okay? Take a break, stretch out, so that your mind is decluttered from all these indices for 5 minutes, and then come back to handle those indices, okay?